shit.
Wait,
Okay.
can I see your answer? I don't know if I got these right then.
Wait, here.
Because I divided everything by 8, but now that I look at it, there are 10 numbers. Crap.
Oh, yeah, 8 is a little off.
No, I have 4.84. That's the data that I got after dividing by 9.
Oh, wait, yeah,
So
so
the crossed out ones are correct, not the boxed ones. Is that?
I'm not sure how you got 8 because the whole, aren't there 10
Yeah,
numbers?
yeah. Because I thought it was 9. But you see the crossed out answer?
Yeah.
I got that one. I divided by 9, so that one's right, not this. One.
Okay.
But then I don't know if I'm supposed to divide it by 10 or 9. Because that's what you're trying
Here, I'll explain it. Okay, so it's crazy. There's so many different things. So we're gonna start, and it's even crazier because population is different from the other one, sample. Okay, I'm actually gonna do 2 colors because I feel like that'll make it easier.
Purple?
Does population feel like a purple or does it feel like a green? I don't know. Maybe it's this. Okay, so the first thing we want to consider, gosh, most of it black. Okay, is the mean or the average. And then for that, like the population, it is. What is the mean or average for a population called?
Mean.
It's called mu. And it looks like this.
Oopsies.
Mu. What about for sample?
Variance. S switches, right?
Not for mean. For mean, it's still X bar.
Just kidding.
X bar. Don't worry. Oh my god. This is like my 7th time going over it. It took me 7 times to figure this out. Okay. The fact that you can do math is like crazy to me. So you're slaying it. You're fucking it up. Okay. And this is called like X bar because it's like an X with a little bar over it. Little bar.
They're the same thing.
No, so they use different freaking symbols for different things. It's crazy for no reason. Okay, and then there's the mean deviation, which we kind of covered today, or yesterday, with the zero-sum principle. Deviation. Remember when she was like doing like, it was like, it was like xi minus mu. And then she wanted that in like, she wanted to add that all up. This, if she asks on an exam, is called a deviation score. And she showed in class that with whatever data set you have, if you add it up, you're going to get 0. Square equals 0. Okay, so principle. And it's pretty much the same with sample, except that is exactly the same, but instead of mu, we're going to use x bar. Does that make sense?
Yes.
Okay, flip. And then, after mean deviation, we have sum of squares. Which she also calls sum of square deviation. And also, just for kicks, sometimes it looks like this, and then sometimes it looks like this. For no reason. They just decided, like, let's give it multiple names. And I was like, bro, why? Why? But, okay, so for population, it would just be like that minus that, and then all that's different is that there's a square there. I think we don't divide by anything yet. And then for this one, it's literally the same, but xi minus x bar, because x bar double means squared. So that's pretty easy. That's pretty chill. And that's just to get rid of like the zero-sum principle thing, because like if I were to draw it out, like imagine like maybe they got this far out and this far out, and then maybe they got this far out and then this far out. If you like average that all up, it would equal, it would balance itself out and it would equal 0. And so what they're trying to do is they're trying to square it. So you get rid of that negative. That negative becomes like this far out, right? Like this far out and this far out. And then so they can add that shit up. And then we go into variance, which you were talking about. Variance. And it's different for each one. I'm just going to draw it out here. It's like exactly this stuff, this sum of squares, and then it's all over n. And that equals this thing called sigma. And then for this one, this is where it gets tricky. It's like sum of squares, right? Right. But then it's like n minus 1. And that's also known as like, they sometimes call this like the degrees of freedom. And like, do you remember her whole explanation for it?
I do.
It was like crazy.
Shuffle.
Like it was the ability to vary. Like if you have like maybe 10 songs in a playlist and you've heard 9 of them, then you can deduct which one is going to be next, right? So that one's not free to vary. Like it has a determined score or determined, number, like song. And so it's like not free to vary. And the whole reason why they do this is because apparently with a smaller sample size, it like messes up the score and it makes it unusually low. And so they're like, okay, well fuck that. We're gonna like make it so you don't have to divide it with so much. Like they decrease the denominator so the entire thing goes up. And then the last one is
standard deviation.
Yeah! Deviation! Yes. Okay. Slay! And so the whole thing is just like, they want it in the original units, and so because we squared it up there, you have to get rid of the square. And so we just do sum of squares n equals sigma. And then over here, it would just be the same sum of squares n minus 1. And that's it.
Can you explain it one more time? Why do we use n minus 1
Yeah.
for sample?
Yeah, for sure. So like, when we're calculating like these variances are just like, I think it's like how far away stuff is or something. But anyways, when you have a population like a whole bunch of people, it like leads to a good average. But if you have a small sample, the average is going to be weird, Like for example, I had 30 kids in the class, and so they all got an average of like an A minus. They got like a 91 average between all of them, and that was like pretty alright. But then once I had like 3 kids in my class, and one got like a 20, the other one got like 100, and then there's this one guy at 60. And so like you're gonna get more error because like what the hell is gonna average just some random ass number? And so they're like, wow, when there are less people, like it sucks. It like just really looks bad, and it like usually is lower than what the variance should be, And so they're like, wow, when the sample size is small, it's unusually low. It's like compressed down when it should be a little higher, Like I would have the average like of this class, like I don't even know, 50 or something, and like that's pretty low, bro. I had a kid that got 100. Like, what's up with that? So they're like, okay, just subtract 1, and then because you're subtracting what it's divided by, I know that's a lot. It goes up.
Oh, okay, I get it now.
Yeah.
You're actually kind of better than the professor.
Yeah, she explains it so quick.
Yeah.
I just can't keep up with her. I have to watch the recordings after class because like she just thinks so fast, but it's okay, because once I get it, I get it.
Thank you so much.
Of
That
course,
helps.
of
That helps so
course.
much. Thank
And
you.
so when you have 30 students, you go with like a better range. It's like, oh, some kid got 80, some kid got 81, some kid got 89, and it looks like a better average because there's like so many. Why they decided on just subtracting one, she wouldn't answer in class. She was like, it's some like calculus procedure, and then she wouldn't respond. So I guess we'll never know why it was -1 instead of -50 billion or minus, I don't know, 2. But yeah. So that's basically why, and then why it's called degrees of freedom. We did the whole song thing. That's how it's different. And yeah, standard deviation. Woo! And so this is just like the operational definitions, because I figured this out this round. Like I've taken this class like maybe once or twice over now, just like watching her freaking videos, and I just realized that there's more to cover.
Oh,
like
it's computational.
Yeah, let me just point it towards that. I started. Okay, yeah. And so like what did we find out today? Like the sum of squares also has like this, right? And then it's minus
N mu squared?
oh yeah, that's one version.
Oh,
That's one version, but I don't like including like any in it. Like it's weird. So like I usually do it like this.
yes.
I think. And just remember here, I don't think you subtract 1.
Because it's computational.
I think so. It's just, it's like it's computational. Oh wait, you don't subtract 1 because it's still sum of squares.
I'm just kidding.
Yeah, you don't start like minusing stuff until you get like lower down. Like this is the cutoff zone. I'll put it this way.
Okay.
So everything above this is just normal, and then after this line, it gets weird.
Why do we use computational like that for? What do you mean by like we have to computate it?
So like, for example, for this, when I do it on my own, I have to have so many freaking rows. I have the original data point, which is like 2, 4, whatever.
Right.
And then I have to subtract it from the mean,
And then square.
and then I have to square that, and then on top of all that, I have to add all of that up,
Right.
and then I have to like, no, actually that's it. But like that's the whole process for this, and this is like so much work. So what they tried to do is summarize it. Like they just said, okay, like take all your data points, and square them. So that's just like, you know, having your data points and then squaring them, right?
Right.
And then the next row is just like adding up all your data points and then squaring that. So it's like less work, if that makes sense. Like, do you see the difference between like doing so much subtraction and then so much like squaring all the way down? I did this manually by hand. I just try to figure it out manually by hand, and I always make a mistake. With this, you make less mistakes. All you have to do is like square it and then add.
Square it and then add. So square it and then add. That's what we're seeing on the left side, right?
Yeah. So so this is that you're squaring it and then adding. Yeah. Here, I'll make it more clear. So for this, you're going here. This is the first point. This is the second point, and then you add it all up. And this is the third point.
Yes.
And so that would be this. Squared, right?
Yes.
So there's only like and then for this one, which is this, we know that we have to add them all up first. It's add and then square. So you just add and then square.
Oh, okay, that's so smart. Yes.
Yeah, it would be like just another like 3-stepper. Instead of writing all of it down, subtracting all of it, and then squaring all of it, and then adding all of that, and making errors around the way or along the way. Like I forgot I accidentally did an extra 8 here, and then I subtracted stuff wrong, and then I squared something wrong, and I made so many more errors. On all of these steps, there's like 4 or 5 steps.
Right.
Compared to like 3. I think that's why they decided to do computational instead. But I don't know why she taught us the OG one then. Like, she was just like, yeah, also learn the operation, bro. And I was like, damn.
She's taught you that so you understand why we use computation, because I didn't understand it till now. I was like, well, what is this? You taught me a whole new thing now. Thank you so much.
Of course.
You're actually so smart. I don't even know how you
I had to like watch so many YouTube videos, bro. It was like so much work. But like I finally figured it out by doing it like literally 5 seconds ago. And I didn't make a single math error. So like I kind of understand why people use it this way. And I was like, how the hell did I not make a single math error? It's only 3 steps, that's why.
Yeah. What's up with n? Because we were supposed to get the same as sum of squares, right? Like, but why is there n there?
Think about it this way. This number is going to be crazy big.
Right.
It's going to be like insane. And then this is just going to be like what we did 67.
Yes.
7. This number is going to be, oh wait, this number is going to be crazy big. This number is going to be insane. And then this one's going to be small.
Oh.
So like, it's kind of like the degrees of freedom. They're like, oh shit, like we can't just subtract it out. Like this number is like what, 4,448? 8, and like the other one was like 448. Yeah. I don't know. Yeah, I think it just like it levels everything out. So instead of being like in the thousands range, and like this number being what, like in the hundreds range, it like puts them in the same range. You know,
Yes.
One is 1,000, and they're like, okay, how do we get rid of like this thousandth? Just divide it by n, and then it becomes in the hundreds, and then they can interact with each other.
Okay, now I see what she meant by computational. You're a genius.
I had to watch so many videos, so thank you very much. It only took me auditing this class like 2 times over. But yeah.
Wow. Okay, and then calculating the variance and standard deviation is the same process, right? Because only getting sum of squares was like different equation, I guess, but
Actually, only sum of squares is the same equation. But yeah, okay, here, I'll show you. I'll show you all of this. And also, don't worry about taking notes because you'll have the video.
thank you.
So sum of squares is easy, okay? We're not doing degrees of freedom yet. It only changes because degrees of freedom. So when we're above this line, everything's groovy. It's the same. Like technically, this is the exact same formula.
Right.
It's not like doing weird degrees and stuff. It's like pretty much the same. Like only this is different. And so sum of squares it reflects that. It's like that, and then minus n. That's just the formula that we use. With variance, it gets weird. I don't know. Does she have a different formula for variance? Let's see. Yeah. So this one's different too.
No.
This one is. Oh my God! Look at that monster.
Or we could just do it on the bottom.
Oh, wow. Okay.
It's probably the same thing, just.
Okay.
Oh yeah, it is the same thing, because this thing is just SS, and then we're just dividing it by that, because if you multiply 1 to SS, it just goes on top of it, right? So we got the SS, which is the formula I drew it down, and then it's just that.
Yeah.
So they're the same thing, just written.
This one's written weird as hell, though. Oh, wait, yeah. This is sum of squares. I see it now. Okay, that makes sense.
Yeah, so.
Okay.
Oh, it's the same as
Okay.
calculating those, right?
This one looks different, bro. This one looks weird.
What's
This one looks
that?
different. That one looks weird, bro. Okay, alright. I'm just gonna start, keep going down. So this is gonna be like the variance, the definitional way. And then this is gonna be variance, what is it? Oh, operational way. Operational. Okay, and so she wants it to be like this, and then this
Minus mu squared.
minus mu squared for no reason. Okay, fair enough.
What does that even mean?
All right, so
Square x, add them all up, divided by the total number, minus the mean squared. What's mean squared? Like, why is that there?
maybe it's too big of a number. I'm gonna stop asking questions. I'm gonna be like, okay, what the fuck? Like, you do you, Tim.
Wait, just kidding. I don't know.
Okay, so if we were gonna try it with our data set here,
Yes.
did we figure out? Yeah, we did. We figured out this number was 493, right? So we know that this number is 493, and then we know that all of it is 10, and then
Squared is.
wait, is all of it 10 though? Because is this a population? Or, no, I think she counts it as a population.
No, in the problem I thought it said sample. Let me check the answer sheet. Oh yeah, she counted as a sample.
She counts it as a sample.
Because
Okay.
it states in the problem.
Okay,
Sample.
Yeah. Okay, slay. So it would be. I would actually put it over here. So it'd be 493. 10 minus 1 equals 9.
And then mu squared is what?
9. And then the average was what? 6.7?
Squared is
6.7 squared.
is 44.89.
Okay. 44.89. And then what's 493? 493 divided by 9 equals 54.777. 54.777. And then that minus this, 44.81.
It's 9. 89.
Minus this. Does that look right?
Variance. I got a 4.45 for my answer. Yours with
4.9? You know what? It's close enough. It's close enough.
Okay.
Let's not worry about it. Wait, 44.1. How'd you get
Well, that's what you got.
Oh wait, shit. I chose the wrong number. Okay, it's 44.1, not 4 billion and 1 billion. Okay.
Divided by 9. That's the minus
1. Equals net.
4.9.
44.1 minus 9. Or, no, not minus 9. 5 by 9. Equals 4. 9, or 4.9. 4.9, and then what else do you have to do? You have to minus mu squared.
No.
Oh.
No, you did everything. That is the whole thing. Oh, you're doing the elongated one.
No, I think that's it. Is that it?
Yeah, that is the answer.
Okay, it's 4.9. It's 4.9.
Yeah, because we're trying to do that, but then we put the wrong number for x,
Okay.
and that's why I was like, oh crap, let's just do that. That's what we did, I think.
Okay, I think that variance and standard deviation, I'm gonna ignore everything up there, and I'm only gonna look at this stuff.
Yeah, me too. I don't
It's
think I could do the
screw that,
longer
bro.
version. Wait, so computate.
I think the only computational difference then is sum of squares.
Sum of squares. Oh, okay, sweet. Good to know.
Because we're ignoring the other stuff. We're ignoring it.
Yes, queen.
Okay.
Hooray!
Oh my god. Okay, now I want you to see if you can do it.
What am I doing?
Scratch this part and this part and write everything down. Here, I'll write you the little structure.
What?
If you can do the mean, what the mean is, the mean deviation, the sum of squares, the variance, and the standard deviation.
I'll just write down the formulas?
Yeah.
Oh, okay.
And then for population and simple.
Swim.
Alright, you got it.
Farm. Yes. Mean population.